In this video, we're going to be discussing the concept of calorimetry. This will be the first tool we have for the way to measure a value of delta H. If you recall from this chapter, it's two pieces. The first half of the chapter, we discuss what delta H is and what we can do with it. And the second half of the chapter is how to actually get these values of delta H. It's something that needs to be measured, and calorimetry is the tool to get that job done. We'll start this process by going over a list of learning objectives in this video. First of all, we're going to review heat systems yet again, the idea of heat coming in and out, exo versus endothermic. I know we've talked about this a couple times, that it really is an integral part of this chapter, and it really plays a lot of roles in a lot of different places. Once we have that idea in our head, we'll then take a minute and talk about calorimeter itself, the actual device used to make these calorimetry measurements. And you'll notice on the right of the screen here, we got a couple different versions of this. A very lab standard kind of one, a single use kind of option, versus down below, this would be an automated device or machine that we'd use if you're doing a lot of calorimetry measurements. Once we understand what the device is, we'll then take some time and talk about how it works. What's happening inside of a calorimeter that allows us to measure the value of delta H for a chemical reaction or the delta H for a physical process. This finally then leads us into the idea of the mathematics that go along with this. From the data we collect from the calorimeter, we are then able to do calculations to figure out that value of delta H. The reason we wait till now to talk about this is when you'll see in these calculations, they're based on a lot of the formulas that we've come up with very recently in class. So now that we have those formulas, we can do the necessary math to calculate delta H from calorimetry data. Just like we started our other videos, let's talk about this idea of a system versus surroundings, the idea of heat moving in versus heat moving out. In this first box over here on the left, we have a reaction or a process that is endothermic, meaning that heat is being drawn from the surroundings into the actual system. Now, just to recap again, the system is the actual reaction, the chemical is reacting, or the object that's changing, and the surroundings are everything around that. It can be the container, it can be the water that your reaction is happening in. Whatever's around that can provide that amount of heat is going to be our surroundings. As a result of the reaction absorbing heat, because it's endothermic, we would expect our surroundings to get cooler. Likewise, we can see the opposite here. This second system represents an exothermic process, either a chemical reaction or some sort of change that releases heat energy from the system into the surroundings. And as a result of this released energy, we would expect this surroundings to get warmer because the reaction itself has gotten cooler. It has released energy because it is exothermic. What I want you to point out now, what I want to kind of highlight for this new direction we're taking this, is the amounts of energy in each process. If my reaction absorbs a certain quantity of energy, then my surroundings are going to lose the same quantity of energy. So what we can kind of say from this is that the energy of our system, the amount of energy that our system gains or loses, should be equal to the amount of energy that's gained or lost from the surroundings. But because it's moving in opposite directions, the system's gaining, the surroundings are losing, and vice versa, we actually have to put in a negative sign here to denote the fact that one side is losing energy and one side is gaining. Again, over here, endothermic means that this system is gaining energy from the surroundings. The amount of energy gained in our system is equal to the amount of energy lost by the surroundings. Over here, since it's exothermic, the amount of energy lost by our system is the same as the amount of energy gained by our surroundings. Now, we haven't talked about this in these terms yet, but I think this is a very logical next step in the thought process here, and it's something we will definitely be needing as we talk about calorimetry later on. So the first major question that we would like to answer is, what is a calorimeter? Well, the important thing to remember is that a calorimeter is simply a measuring tool, just like a ruler or a volumetric flask. It's a device that allows us to measure the amount of heat that goes into or out of any type of process. That process can be a chemical change, in which case our calorimeter will measure the delta H of the chemical reaction involved, how much energy is released or absorbed, and we would denote that as delta H of reaction. Or that process can be a physical change, and we've talked about a couple of these already. For example, we brought up delta H of vaporization and delta H of fusion. These are the energies involved in boiling something and the energy involved in melting something. And this can be measured with a calorimeter. How much energy does that take? Something we haven't discussed yet would be delta H then of solution. How much energy is absorbed or released when a substance dissolves in water. Calorimetry does not care what type of heat process is being undergone. It just matters that we can measure that heat change and use some calculations to figure it out. So calorimetry will work for all of these. The way we're able to make these measurements is by measuring the temperature changes in water that are due to the heat that's being either absorbed or released from your process. We cannot measure heat energy directly, but we can measure temperature changes directly, and as we've seen in previous videos, those two things are related together. As the temperature of our water goes up or down, we can correlate that back then to a certain quantity of heat that was absorbed or released in our process. To do this correlation, we use the equation we've already introduced, Q equals mc delta T, which then allows us to relate how much the temperature changed to a certain quantity of heat that was absorbed or released in our process. The last piece of the puzzle then is that we assume the heat energy coming out of a reaction is actually the same as delta H. Now, as we've talked about earlier in this unit, delta H is actually equal to Q, which is the heat, plus the amount of work done. The way we're able to make this assumption here is that we create a situation where the amount of work done is about equal to zero, or as close to zero as we can get it, which allows us then to say approximately that the delta H of a reaction is approximately equal to the heat energy that our calorimeter is either able to absorb or release. Just to wrap up our discussion as to what a calorimeter is, here we got a couple of photographs of some calorimeters of varying qualities and uses. The ones we'll be working with here in class are simply these guys down here. This is a styrofoam cup calorimeter. We take two styrofoam cups, we place our reaction or our sample on the inner cup here, and we have an outer cup for insulation. Inside of this, we put a device in that allows us to stir, and a second device in that allows us to read temperature, and we'll be able to measure the temperature change in water based on whatever's happening in here. This is a higher quality version that obviously has a little more engineering put into it, but it's basically the same setup. We have a device here for stirring, we have a port here to allow us to put in a thermometer, and then we have a reaction container to run this in, again containing a good deal of insulation. Over here, as we talked about earlier, this is more of a lab-grade, high-throughput device. This allows you to measure a lot of calorimetry measurements in a shorter span of time, but it's the same thing. Notice here we got that same large steel container for doing our reaction in. It's going to have water that's going to change temperature as a result. The thermometer and stirring devices are built into the machine itself, and this machine will probably take samples on its own, load the calorimeter on its own, make the recordings on its own, and then by the end of a process have many measurements done as opposed to one. Clearly, just by looking at these gadgets, we see that as we go from the simplest to the most advanced, we end up spending a significant more sum of money, and that more money is buying us a higher quality equipment that gets us better answers, and it's also buying us convenience, which is what you get over a device like this. It can do a whole day's worth of work in a couple of hours. What you'll notice that they all have in common is this right here, the idea that they're heavily insulated containers. If we're measuring the amount of heat that's happening in our reaction, making sure that heat stays put is one of the most important pieces. And we'll talk how that plays a role into the quality of our calculations a little later. Now let's change gears a little bit. We've identified what a calorimeter is, and now it's time to talk a little bit about how a calorimeter works. I would take a minute right now, pause the video, and get a rough sketch of the picture I have here. That way we can talk about that sketch and kind of describe what each of the pieces is doing and what they're responsible for. Alright, now you should have a sketch of this thing drawn in your notes. It doesn't have to be pretty, it just has to have all the pieces present with the appropriate labels. The first thing I'll point out is that this is a particular type of calorimeter known as a bomb calorimeter. And this one is specifically designed to measure the delta H values of combustion reactions. So the way it works is down here we have the actual reaction vessel itself. And here's where you would put your sample. In this case, it's in this little dish here at the bottom. We've got these ignition wires here, which allows us to pass an electrical current, which will cause ignition to occur. And we've pumped in a significant amount of oxygen, which is one of the necessary ingredients for a combustion reaction. When this reaction is started and the ignition starts, what's going to happen is the heat coming out of this combustion process is going to radiate into the surrounding water in the tank itself. And as a result of it radiating in the water, the temperature of our thermometer is going to rise. The amount of temperature increase that occurs must correspond back to the amount of heat energy that came out of the combustion process here. So let's actually jot that bit of information down. The change in temperature in our water is linked back to the amount of heat released from our reaction. So in terms of data then, we would record how much temperature change occurred on our thermometer. We would record the mass of the water from our sample. We would record the mass of material we have here from our reaction, and we take all of that information and plug it into our equations from before, which I'll demonstrate in a second, and that would then allow us to calculate how much heat energy was released from the reaction down here. Now again, just to recap something talking about before, this all works under the assumption that no heat escapes. And that's all based on the quality of insulation around this container here. If water heat energy does start escaping from the water into the surroundings, that's heat energy that won't cause our thermometer to rise, and as a result of that, we'll end up getting some data that's a little bit flawed. We'll end up getting a smaller value for delta H than we really should be. Therefore, again, the quality of the calorimeter you get, one of the measurements is how insulated it is. The better that insulation, the better quality results you're allowed to calculate. Now this then allows us to turn the corner from how the calorimeter works to how the math on the back end works. So now that we've collected data from our calorimeter, we can calculate the actual delta H of our reaction. Just as we've already said, but we can put it on paper now, the calorimeter really consists of two parts: the reaction vessel itself, which is the system, and the water reservoir surrounding it, which acts as the surroundings. The assumption, again, that makes this work is that no heat escapes the process, meaning, and this is the real key point here, all the heat energy that comes out of the reaction goes into the reservoir and vice versa. So basically, all of the heat that comes out of here, our system, has to go into the surroundings. If no heat escapes, then we have a very accurate way of keeping track of how much heat came out of our reaction. Just like we already said, we can use the equation Q equals mc delta T to relate the change in temperature of the water back to a quantity of heat that must have come out of our reaction. And we can use this equation to calculate that heat for both parts of the process. And we can see something like this. The heat that is absorbed by the water, it corresponds to the mass of water used, the specific heat of the water, and the temperature change from the water that we get from our thermometer. Likewise, the heat from the reaction corresponds to the mass of material in our process times the specific heat of that substance, and then finally the delta T of our process as well. And we can think of this as happening as two separate things, and again, we can get all of this data from the actual calorimeter itself. Now, to tie all of this together, the real question you want to be asking is why does the water change temperature? Why does the water heat up? And the only answer to that question is because of the heat from our reaction. The only thing that's causing that water temperature to rise is the heat of the reaction. That therefore allows us to mathematically link these two things together. We can say that the heat that goes into the water must be the exact same amount of heat that came out of the reaction, again, assuming that the reaction is properly insulated. Now notice we also include this negative sign here, and remember the sign denotes direction. Because the heat is coming out of the reaction and it is going into the water, we have to pop in that negative sign to make the two of these things equal. One of them will naturally be negative, one will be naturally positive. To allow those negatives and positives to cancel out, we have to add this extra negative sign in. However, this doesn't really do a whole lot for us. Instead of writing Q water and Q reaction, let's substitute the mc delta T's into this equation and get something a little bit more important. We can see by replacing Q with mc delta T and Q over here with mc delta T that we actually have some variables we can work with here. Now, if we record the mass of the water and the mass of our sample, if we record these, or we look up, I should say, the specific heat of the water and the specific heat of the sample, and we can record the temperature change of our water and the temperature change of our sample. If we record any number of these things and we have one missing, we could calculate that missing value. This would be true if we had a physical process where something is just getting hotter or something is just getting colder. In a chemical process, we would use this version of the equation, and it's basically the same thing. The only difference is here I just substitute the MC delta T for the water, and I leave the Q reaction by itself. So if I knew the mass of the water in my calorimeter, I do always know the specific heat of water, that is 4.184, and then I can use the thermometer to measure that delta T. The amount of energy absorbed by the water must be the same as the amount of energy that came out of our reaction. And if you recall from earlier in our discussion, this value is then equivalent to the delta H of our reaction. So from this key idea, this idea that the amount of heat going into one is the same as the heat coming out of the other, we can generate two very similar equations, one to calculate certain values in a physical change, things like specific heats of an unknown, or one to calculate the delta H of a reaction in a chemical change. We can just use the water data, use delta H of reaction, and finally determine, or find Q for the reaction and use that to determine delta H for our reaction. Tomorrow in class, we will have some examples as to how to do this. We'll do some problems together, and we will also take some time actually to dive into a lab where you guys are going to make these measurements with a calorimeter and compare the results you get to known values of either C for the specific heat of an unknown or the delta H of a reaction. Just to summarize the video, the question you should be asking now is, what should I be able to do based on the knowledge that we've just gone through? Well, first of all, you should be able to explain the purpose of calorimetry. What is the process used for, and what is it able to measure for us? And if you recall, it allows us to measure the delta H of some sort of process. You should be able to describe the parts of a calorimeter, what are all the parts involved, and you should be able to describe the role that each of those parts play. Why are all those pieces in place? And all together makes a calorimeter work the way a calorimeter should work. And finally, you should use the idea of conserved heat, the fact that the amount of heat coming out of one reaction must be the same as the heat going into the other reaction, to allow us to calculate a bunch of different values. For example, we talked about how we can use the chemistry version or the chemical version to figure out delta H of unknowns. We can use the physical version to calculate the specific heat of unknowns. And then depending on the situation we're in, if it's just a regular old class question, we can really solve for any of the missing variables in this equation based on other calorimetry data that's provided for us. This definitely something, though, is we need to practice in class a little bit more. You should understand how these things work at this stage in the game, but maybe need a little more time talking about the actual application, doing the problems on your own.